Thanks very much for having me today. I would like to talk about an observation campaign that we did jointly with other telescopes on a specific FRB. And essentially, that's a bit like a continuation of a talk that I gave at the 2021 Eastern Conference when I reported about our first fast radio burst observations. And at that time, I talked a bit about what is the motivation to do these observations. I talked about the first detections that we had. And I also talked about at that time about how do we actually observe that? What is the processing pipeline? How do we calibrate and so on? So I'm not going to repeat that, but rather I would like to sort of continue from there and talk about what happened after that. When we started a high cadence long-term observation of this fast radio burst, which also led into a cooperation between ourselves and several other institutions. And I would like to talk about today about the science results that we are getting from the data that we have collected. Just a few words about what are fast radio bursts. Vikram, of course, has earlier today talked about that quite a bit. So it will be a little bit of repetition of what he already said. Simply speaking, fast radio bursts from an observational point of view are single pulses. They are broadband, cover a wide spectrum in the radio regime. And their specific characteristic is that they have a high dispersion. That means that higher frequencies come earlier than the others. And that gives rise to the idea that they must come from large distances. And I'll explain that a bit in just a moment. The whole story about FRB started by a detection by Duncan Lorimer in archival data from the Parkes telescope. It was called at that time the Lorimer burst because that was the only event that was known. Today it's called FRB201124. And you can see again this dispersion in the curve where the higher frequencies arrive earlier, and only if you de-disperse that, you actually see the pulse. So de-dispersing means that everything is shifted, so it comes all at the same time later in the post-processing that's done. Okay, why do we think they come from large distances? If we look at the dispersion, that's caused by charged particles, mainly electrons. And we know dispersions from pulsars in our own galaxy, and so that's a known phenomena. What we do know from various observations is what is the electron density in our own galaxy. So if we do an observation and if we find a pulse that has a much higher dispersion than can be attributed to our own galaxy, then they must come from somewhere else. And the idea is that there's a source, a fast radio burst emitting in another galaxy, and then you have a contribution from the own galaxy, the electron density there, and then all along the way there are other electrons, and then again our own galaxy. As I said, the main thing is if it's larger than the contribution from our own galaxy, it has to come from somewhere else. You don't quite know how far it is because you do not know the contribution from the host galaxy, but at least you know it's coming from somewhere else. The source, the actual phenomenon that creates these bursts is not known at this point in time. Vikram has already clearly stated that. We do not know. There are some thoughts it might be magnetars, but that's still an open question. Originally, and during the first things that were observed, they were thought to be one-time events. So one has seen an event and people try to look at the same location and see if it happens again. And in most cases, it didn't happen. However, at some point in time, Laura Spittler used RSIBO data, and she found actually a FRB that did repeat. Repeating means it's the same location and it has the same dispersion measure. So it is the same source, most likely at least. And ever since this first detection of a repeater, there have been more repeaters detected, quite a few number, many of them by the CHIME telescope, but also by others. There's one observation that was made that some repeaters show an episodic behavior. That means that there are periods of activity, and then they are sort of silent, and then they come up again. And even in some cases, this episodic behavior comes regularly. So there's a certain repeating pattern in the episodic behavior. But all this is observation, phenomenology, but the actual source is not known. The specific FRB that I would like to talk about is called FRB20201124A. Why is it called this way? Because that's the date when it was detected in 2020, November 24th. And it was detected by the CHIME FRB collaboration. The CHIME telescope is very well suited to detect FRBs because of their great field of view. And it was soon detected that this is a repeater. The dispersion measure of this is given there in the 410 range. So that's definitely much more than you can expect in that direction from our own galaxy. So it must be a FRB coming from somewhere else. Because it's a repeater, there were interferometry measurements which allow to determine the host galaxy. So we know which galaxy that guy sits in. It's a complicated name, but that's how it's called. And there was a enhanced activity, one of these periodic events where more pulses come in a short period of time. That was reported in an astronomer's telegram by the CHIME collaboration that came out on the end of March, and that triggered observation by us. I talked about that in a previous talk, so that was sort of the trigger for us to go after it. And we had our first detection on April 15th. It was a very strong pulse. We had a signal-to-noise ratio, even with our moderate-sized dish of 25 meters, we had a signal-to-noise ratio of 45. And we determined a certain fluence, which is also very large. Again, the detection plot is shown here on the right. Now, what happened after that, we issued a astronomer's telegram because it was such a strong event. And this and some other talks with the radio astronomers from other observatories triggered a multi-telescope observation campaign. And this is essentially the core of my talk. Who was involved in this campaign? There are 4 telescopes in total. The largest one is located in Poland, in Torun, operated by the University of Torun. Then there's another 25-meter telescope in Onsala in Sweden, operated by the Chalmers University. Then involved was one of the 25-meter dishes of the Westerbork Observatory, operated by Astron, and then our own 25-meter dish, operated by us, the Astropeter Stockard team. So these are the telescopes that were involved in this observation campaign. I should mention these were not interferometry, so these were run independently. We did not have the possibility to correlate that to do interferometry. The characteristics also are a bit different, or the observing band. Torun has the possibility to observe in C band as well, besides the L band. So in the 4.5 roughly gigahertz range. Onsala has 2 different L band observing ranges listed here. Different bandwidth. And Westerbork also had 2 different frequency ranges which were used. One is in P band in the 300 to 364 megahertz, and then again L band. And ourselves, we can only observe in L band, or we can observe around 400 megahertz as well, but this is so much disturbed by RFI that we simply don't use it for that purpose. So we have 4 telescopes with slightly different observing bands. And we observed in the time period between March 2021, that was our first observation. That was sort of the trigger of the campaign, all the way through for 1 year until March 2022, I should say. We had a total of 3,500 hours of telescope time. So this is very massive observation. If you think about 3,000 hours, that's quite a lot. And that meant that we had 2,280 some hours on source. Why is there a difference? Well, there were times when we were observing simultaneously with 2 telescopes. So we had 1 hour from one telescope, 1 hour from another telescope, but it was 1 hour on source. Our own contribution was actually the largest from all the telescopes. We had 1,400 hours roughly of observation time, so quite a massive effort to observe this one and only target. During this whole period, there were 60 overall detections, but because sometimes we observed something simultaneously, there were 46 different pulses. So during this period, there were 46 pulses detected in that 2,200 roughly hours on source time. So as you can see, they are not that frequent, but one has also to see that because of the sizes of the dishes in the 25-meter range, we are seeing essentially the tip of the iceberg. We are seeing only the strongest pulses. But this gives some interesting science results because of the long observation time, as I will explain towards the end of the talk. A little bit looking into the details here. These are the different observing bands and the observing hours. I won't go into any detail here, but I would just pick out 2 things from this list. The different system equivalent flux density of the telescopes. The system equivalent flux density is what flux density do I need to get the same signal as my noise background, so a 1-to-1 noise background. And as you can see, this is in the range of 300 to 400 for the 25-meter telescope class, with exception of ours. And you see there are 2 different numbers. We started with our, let's call it the standard setup, which gave us a 1100 Jansky system equivalent flux density. The other telescopes all have cryogenic receivers. And we made a change to one of these low noise amplifiers that Wolfgang mentioned, which are developed by Sander Weinreb. We were fortunate enough to get one of those, or 2 of those. And we replaced them, and then we were on the ballpark of the other telescope. That again shows what Wolfgang has alluded to, excuse me, that these low noise amplifiers developed by Sander Weinreb bring your telescope in the range of what others can only achieve with cryogenic receivers. And consequently, there's another value, the so-called completeness. This is a number, is how intense must a pulse be to be safely detected. If it's below that, you may miss some. So we're in the same ballpark now as the others. Anyway, so this is the total observation time. If we look how that went over the period of time, the top graph is showing the time period from March 21 to January 22. And I have to explain that a bit. The colored vertical lines, they denote the observing frequency range and the times that are covered. Our own contribution is the violet one. As you can see here, this is our 100 megahertz of bandwidth, and these are all the times when we have observed, and you can see the other telescopes, how they fit in. The black lines are the detected pulses. So you can see that we had a cluster of observation or successful observations in the first period. And then there was a period of silence where we did not observe any more events, with exception of a short period here. And then the second graph shows from January 22 until March, so a shorter time span than the one above. And then again, quite a number of successful observations. What you can also see that we had a gap of our own observation from here all the way through essentially beginning of February of 2022. This was a time when we had maintenance, and this is also the time when we replaced the LNAs to have the more sensitive LNAs in our setup. So we could only start observing. We were very eager to start because, as you can see, there were detections, but we were not ready yet. So we wanted to get ready very quickly, and then this is the remaining thing. So this is how it worked out for us. The evaluation of the event, each event was evaluated. So what we looked at was the time of arrival. And in order, because we need to correlate the different observatories, everything was referenced to the Solar System Barycenter. Obviously, we had different observing frequencies, we had different locations, which means that there's a time of arrival difference. And in order to determine are these exactly the same events, when we see something, we reference it to the Solar System Barycenter and also to infinite frequency. Of course, we looked at the signal-to-noise ratio of the different pulses, and then we also looked at the fluence, which is the total energy of the pulses. So it's essentially intensity multiplied by the time. Then, as we can see in a moment, there are different components sometimes. It's not just a single pulse, it can have a certain structure. We looked at the number of those components, the width of the pulse. And then we looked at the spectral luminosity. That is a number which sort of gives you a measure of the energy that's released from that particular FRB. In order to determine the energy, you need to know the distance. We took the localization from this specific galaxy, so we knew it was 450 megaparsec away. And also you have to make an assumption whether it's a beamed emission or an isotropic radiator. It's very common to use an isotropic radiator model. So that's a number that you come up with, which gives you an idea of how intense is it actually. And then there's another aspect, which is the scintillation bandwidth, the structure that you have in the frequency. So this is what we all looked at. The few examples, I want to show you some of the observations. This is the most luminous pulse, or the one with the most energy in it. It was detected actually by our telescope. And as you can see, we had a signal-to-noise ratio of 114. And the intensity, the luminosity, was 1593 Jansky milliseconds. To put that in comparison, that's a bit wider than 1 millisecond. It's a few milliseconds wide. So just for comparison, it's about a little bit less than the brightness of Cassiopeia A. So this is as if Cassiopeia comes on for a very short period of time. This is the most luminous example. Some other observations. This is one and the same pulse. You can see the time of arrival is practically identical. It's within microseconds, I believe, identical. The left one is an observation by the SARA telescope, and the right graph is showing our observation. Now, you see one thing is interesting, that the structure from 1.6 gigahertz roughly to 1.46 gigahertz is different than from 1.4 to 1.33. This is our range. So essentially, this is sitting on top of this. And you see that there is a very strong variation of the pulse with frequency. And that is something that we have seen very frequently, that is the observation or the structure of the pulse is frequency dependent. As you can clearly see, there's a precursor in the SARA observation, and the precursor essentially has disappeared, whereas the postcursor here has become more developed at the lower frequencies. So it's one of the characteristics that can be clearly seen. This FRB, and it's not the only one that shows this behavior, it is not completely uniform over the full spectrum. Then there are cases when you have a multi-component structure. You already see a bit, already see a bit of that here, but this is a very extreme example where you have really a couple of distinct pulses clearly separated from one another. The total time span is 75 milliseconds. So there are short pulses coming in within just a few milliseconds. And yet another example, again, one of our observations, and in the beginning, we weren't quite sure whether it is actually a FRB, but we determined it actually is. You can see our 100 megahertz of bandwidth, but the FRB shows only a fairly small part of the spectrum, about 20 megahertz wide, and you can see some structure of scintillation there. Again, a sign that FRBs, their luminosity over frequency can vary quite a bit, and it's not something that is, let's say, typical for one specific FRB. It varies all over the place. Yet another observation example, again comparing a pulse which was observed by both the Stockard Observatory and the Westerbork Observatory. We call this one the Trident of Poseidon, so it's a triple pulse. Both observations have a triple structure, but it's still different. What you can also see here is what is typically called the sad trombone effect, that is maybe shown here. This one sort of dies away and these one come up, which means that over time, emission migrates from higher frequencies to lower frequencies. This is called the sad trombone effect, and something which is very common in FRBs, particularly in repeat FRBs. There's actually some discussion whether, if you see a sad trombone effect, whether that is an indication of a repeater, but that's not confirmed yet. All right. What are the key findings from that? We have seen that this FRB has an episodic behavior. We have seen pulses with a very high luminosity. Another interesting aspect was, as you may recall, we had observations also at P band and at C band, but we did not detect any pulses in P band and C band. Let me just go back a bit. So we had these observations here in P band, and we had these observations in C band, and also here. And whenever we had a detection in L band, and we had a simultaneous observation in C band and P band, we only detected it in L band. So it, again, is a sign that it is spectrally confined, the emission. Okay, going back, slides. Okay, so only pulses in L band, a strong variation of pulses over frequency, that I have shown in some of the examples. The occupied bandwidth is only a few hundred megahertz, but can be as low as 20 megahertz, as we have seen. We see a great variety of pulse shapes, including multiple pulses. And I should also mention that we detected no periodicity. I mean, one of the questions is maybe FRBs are magnetars, which every now and then emit a very strong pulse. This is known from magnetars that they can emit in between their normal pulses some very high pulses, just like giant pulses. But in this case, there should be a periodicity. If it's a magnetar, it should be rotating. And all attempts, this is not only in our observation here, there are probably much better observations that look for that, more sensitive observations. But up to date, there has been no periodicity detected, which means that the idea that FRBs are magnetars is not supported yet by an observation like that. And another interesting finding was, and I'll explain that a little bit more in a moment, is that high energy pulses are more frequent than you would predict by a simple log normal distribution. And what that means, I'll show in just a moment. First of all, on the episodic behavior, we had this period from April to May, about 6 weeks, when we saw a lot of activity. Then there was short activity when all of a sudden we had 4 observations or 4 events on a single day. So they all occurred on a single day. And then we had a period starting late January until early March, when there was again a period of high activity. And I can confirm that after that, we continued observation a little bit beyond that, that the activity has died. I should also mention that we have tried to predict if we have a period of activity here and a period of activity there, maybe if that's regular, when would the next period of activity come up? Was predicted somewhere in October, November timeframe of last year, and we did not see anything. So it's episodic, but not confirmed to be periodic. The a question that we asked ourselves in the analysis was, since we have very strong pulses with a very high isotropic energy, we looked at our strongest pulse, and there is a theory of a maximum predicted energy by James and his co-authors, and our isotropic energy actually was close to that predicted maximum. So whatever that means, that's a finding. Another question that we ask ourselves, given the fact that we have these strong, very bright pulses, and if we would not use a 25-meter dish, but rather use a 500-meter dish, how far away could that be? So same isotropic energy, but then looking with a 500-meter telescope. The answer is, the calculation is, the redshift of that would be 12. So very, very at the edge of the university, at the edge of the universe, not at the edge of the university. There's a caveat though, because of the redshift, the emission to be detected here in L band would have to be at 19 gigahertz, and it's unknown that fast radio bursts emit at such high frequencies. But at least it's an interesting thought that if that guy would sit at the edge of the universe, we could actually see it with a fast telescope. The fact that I mentioned, which is another kind of interesting finding, is I mentioned that our telescopes in the 25-meter class, we only see the tip of the iceberg. So we only see the bright ones. And there was an observation and a publication from observation by the FAST telescope. And when you use that data and plot it against the frequency or the probability of occurrence versus energy, you see a slope. So the higher the energy, the lower the probability. So in other words, the higher energy pulses come less frequent. And you would expect that if you come into the regime of our detection limit, that there would be, if you extrapolate that, there would be less frequent than they actually are. So the finding is that high energy pulses are more frequent than it can be expected. So must be some kind of a curvature or takeover or whatever you want to call it, that high energy pulses are more frequent than you would expect from the low energy observations. Having said that, this is also the motivation why we do it with the small telescopes, because we can afford to have such long observation times. You need long observation times to get these very high energy ones. With telescopes like Effelsberg and FAST, you simply cannot afford to spend thousands of hours on one single object, which we can do. So the FAST telescope cannot explore that energy range because they're too less frequent. They cannot afford to spend that amount of observation time. So this is an interesting finding, and of course, again, since the nature of FRBs is not known what they are, there's no explanation. It's just an observational fact, and I can disclose that we are doing similar experiments on a different FRB, and it seems to confirm the same behavior on a different FRB, that high energy pulses are actually more frequent than predicted from the extrapolation of low energy pulses. So comparing what we find with other repeat FRBs, episodic behavior is something that's very common. Episodic behavior is seen in the first ever detected repeater, but in many others as well. This FRB, however, is exceptionally bright, so we do see quite a number of these very bright pulses where they are even bright for a 25-meter telescope. So they are really, really bright. This strong frequency dependence is also common among FRBs, among other repeaters, when you say, okay, if I look at the spectrum, how does it behave? That's very common that you have a strong frequency dependence. And as already mentioned, the periodicity, we have not seen any periodicity, and the same is the case from any other studies with FRBs. And as I mentioned just a minute ago, we are now looking at the high energy pulse distribution by the same group of telescopes with another repeat FRB, which is bright. And it looks like that we get a similar result. So it seems to be something that is characteristic of these types of FRBs. The whole story will be published hopefully soon in Astronomy and Astrophysics. And I should mention that, of course, this is a work that is, because there were so many other telescopes involved, was not something that was done simply by us, but there's a list of different people who have worked on that. I've listed them here in the sequence as they appear in the upcoming paper. I guess one of the key people was Omar Old-Bocatina, who did his master thesis on that, and Franz Christen, he did most of the writing of the paper, and we contribute most of the observation time. So we did contribute quite a bit. Anyway, so this is a large team, mostly from the Astron, from the University of Amsterdam, from the Orbital Space Observatory, and from the Turun Observatory, Nicolaus Copernicus University there. And it was really fun doing this joint observation, exchanging the latest FRBs observed via Slack, and discussing things, what to do and what to do next, and scratching the heads jointly. So it was an interesting exercise, and I'm looking forward to do more things in the future. Well, that then concludes my talk for today, and I'm happy to take questions. I can't see the chat right now, so let me see.
Okay,
yes.
I'll help you out here. Let's see. This is from Hermann Wegeler.
Yep.
Wolfgang, could gravitational lenses explain the distribution of the pulse energy observed at the high energy end, and could this maybe be a reason for the force sample on a day?
I haven't thought about that. Gravitational lensing, let me put it this way. There are some ideas that FRBs, that there is a lensing effect possible, and it could be gravitational lensing. It would have to be a gravitational lens which is very short-lived. We know that from gravitational lenses that they do exist. I mean, they're optical observations, and if you observe them today, the lens looks the same the next day, and so on. So this is a very slow varying effect because we're talking about large structures. A change in the gravitational lensing on a day time scale, I would find that unlikely. Whether you have, let's say, a gravitational wave that does lensing, I would say the chance of that happening is very, very low. So physics would not exclude that, but it's probably unlikely.
I do have a question about, since we're doing all this maser work on the SARA list group, is it possible that a pulsar burst could actually cause a maser effect that would excite a bunch of stuff, and we'd get that signal out?
What speaks against that is the fact that they are broadband. And a maser would be fairly narrow band. You could expect, of course, that due to, if it's an extended area, that you have different Doppler shifts and so on. But I would expect that any maser emission would be fairly narrow band, and it has to be in the vicinity, the frequency has to be in the vicinity of a known transition of a molecule or atom. So answer would be not very likely.
Okay, thanks. All right, no more questions over here at the Owens Valley. Anybody else have any questions? Well, great talk, Wolfgang, and looking forward to more stuff. Yeah.